Again, welcome everybody to the String Theorem seminar series, and sorry for the delays with the Zoom link. For today's first talk, we're very happy to have Lorenzo Paoloni from IFT Madrid, who will tell us all about curvature divergences and gravity decoupling in Calabi Yau. Please take it away.
Thank you, Filippo. Thank you, Bruno, for giving me the opportunity to present in this seminar series. Today, as Filippo was saying, I will talk about curvature divergences and gravity decoupling in Calabi Yau rigid limits. That is also, wait, can you, oh, too much. Here it is. That is also the title of this work done with Alberto Castellano and Fernando Marchesano. This paper was out in February, but this paper has also a big problem. It is very long. It is very long. And let's be honest, nobody wants to read a 100 pages long paper with equations that look like this, of which, I mean, fair enough, I'm totally responsible for this kind of equations. But for this reason, I decided to ask to give this seminar to advertise a little bit this work. And my goal for today is to provide you with the idea that is behind this paper and to show you what are the quantities, the objects we look at to convey this idea. And so that you can be more familiar with these objects and hopefully approach the paper with more ease. But so let me start by a little bit of years ago with Fernando and Luca. We put out this conjecture, this curvature criterion, proposing that divergence in the moduli-space curvature signals a corner in the space of theories where gravity decouples. The setup we studied was type 2A string compactification on Calabi triples in a large volume regime and following the so-called EFT string limits. So first thing we do with this in this work is study this criterion in more general setup. We want to try to, well, we want to test this criterion in more general setups, but it's not only this. In fact, I would say that the attempt of this paper is to build a net that connects between different clues, as if this was a case, clues that all point at the same direction, of the same suspect, that is the decoupling of gravity. Specifically, in this paper, we connect curvature divergences, charge to mass ratio, divergences, monodromy, factorization, flow of EFT couplings, and metric essential instanton. This today, unfortunately, I won't have time to touch this, but it's one of the main topic of the paper, and it's actually very, very interesting and very insightful. But the important thing is that all these concepts are found under the same umbrella. They are all linked to gravity decoupling. But as you can imagine, these are various concepts and in general are very different. I will first introduce some of them in a very general way, and then I will be more specific, but I will do it with the help of an example, a very celebrated one. But let me start by the secret that is behind the connection of all these quantities you are seeing here. And that is the setup that we consider. So let's have a look at the setup. We always take four-dimensional n equal to 2 supersymmetric theories, and we are always interested in the vector-multiplet sector. Then when we talk about gravity-coupled theory, a supergravity theory, we mean a theory describing the dynamics of n vector multiplets and one gravity multiplet. While when we refer to a gravity-decoupled theory, we mean a theory describing the dynamics of only vector multiplets and no gravity multiplets. So a super EMS theory. Now, a common feature of both, if we look at the action, is that the vacuum expectation values of the scalars are free to choose. These fields are moduli, and their vevs describe a space of theories. This is because the coupling, and not only that, as we will see, in these theories will depend on these vevs, and moving on this moduli space literally changes the parameters in the theory, as if we were tuning them. So this is important in this talk because a gravity decoupling limit for us is a trajectory in the space of theories that brings a subsector, well, a theory, or better, a subsector of the theory that is coupled to gravity to look like a theory that is decoupled from gravity. The trajectory in the moduli space that interpolates between these two actions, once we restrict, of course, to the right subsector, is called the rigid limit. And I will refer to the super Mills theory as rigid theory. This already allows me to introduce the first point in this net, the first condition to start to have a look if we want to claim gravity decoupling. In fact, from here, we immediately understand that a trajectory in the moduli space must be making a subsector of the theory of its very couplings to look like a theory without gravity. This is then a consideration about the EFT action, and it's somebody that we can check directly from the couplings. Something that if you give me an action, I can compute and give you an answer. But for this condition, let me leave this condition here and not being more specific. I'm going to be back on this at the very end when we will have an example in front of us, because I think that this condition that we are asking is more understandable if we are looking at an example. So I want to talk about another point in this net. And to introduce it, I have to introduce something that we cannot see explicitly in the action, but that nevertheless determines any of its parts. I'm talking about the period vector. There is a feature, again, that is common in all four-dimensional n equal to 2 supersymmetric theories, being these supergravity theories or super EMS theories. The names come from the fact that the entries, as we know, are can be thought as integral of a form over a cycle. In its importance, it's twofold, let's say, because as I said, it is sufficient to recover all the couplings in the 4D action that I showed you before, but it also gives us information about the massive spectrum that is charged under the U1 fields. Since we are interested in starting from a theory with gravity and take a limit to decouple gravity, let's consider the period vector of 4D n equal to 2 supergravity. In the paper, we consider type 2B, string theory, string compactification on Calabi Yau threefolds, and the period is obtained by integrating the holomorphic treeform of the Calabi Yau over a basis of 3 cycles of the same. So the entries are literally the volumes of the 3 cycles. In this setup, wrapping the three branes over these cycles gives BPS particles, and their mass can be extracted directly from this period quite easily. In this sense, given an electric and a magnetic charge, the period defines a map between, well, from these integers to the mass of the corresponding BPS state. Now I want to take advantage of this discussion and, as I said, introduce another necessary point in our gravity decoupling picture, the divergence of charge to mass ratios. In fact, if a subsector of the theory is decoupling from gravity, we expect that there should exist massive states that are charged under the rigid U1s, for which the electromagnetic interactions are much stronger than the gravitational ones. So here, in this no force relation between BPS particle, the electromagnetic interaction are identified, are measured by the physical electromagnetic charge and the gravitational interaction by the mass, of course, of the BPS state. And so to measure the ratio between the two interactions, we can simply taking the ratio of these two quantities. And we expect that along a rigid limit, there should exist states for which this ratio diverges, for what I just said. This is another point, as I said in our net, but it is not the last one involving the period vector. To introduce this point, that will be the monodromy factorization. I need another general property of for the n equal to 2 supergravity theories. Well, n equal to 2 supersymmetric theories, sorry. That is that for any isometry of the scalar manifold of the moduli, the period transforms under the action of the symplectic group. In particular, for a theory coupled, yes, a theory coupled to gravity, a supergravity theory, with the n vector multiplets, this group will be of rank 2 times n plus 1 and valued over the integers. But we are interested in particular, a very particular specific transformation in the scalar manifold. We are interested in the monodromy transformations. What I just said simply means that for each of these transformation on the coordinates of the moduli space, the period vector will be rotated by a symplectic transformation. And composing this symplectic transformation, we obtain what is called the monodromy group of the theory. But why am I stressing this? Because as I told you, this is a property of both supergravities and super-Yang-Mills theories. And so if we want to claim the coupling for a subsector of the theory, we should also ask for factorization of this monodromy group that do not mix what we identify as the gravitational direction and the rigid field direction. This is because the decouple theory should have its own closed monodromy group. So this factorization condition and the divergence of charge to mass ratio, we believe, are necessary to claim full decoupling. And for this reason, we named as core rigid field theory the subset of electromagnetic pairs of 3 cycles with divergent charge to mass ratio that are also closed under the action of the monodromy group. So just to recap, so far we have introduced these 3 ideas. We saw how these are connected to gravity decoupling. But as I said at the very beginning, now I want to expand a little bit more. And to do so, I will consider a specific example, specific type 2 string compactification on a well-known Calabi Yau. And yes, so we are going to take what is called a geometric engineered rigid limit. So I'm gonna explain what I mean in a second. Well, first of all, let's say why this is an interesting example. Well, first of all, because it is one of the most studied and understood gravity decoupling limits. It is a well understood Calabi Yau, and also it exhibits all the feature I already mentioned in a very clear way. Well, actually, so clear in such a clear way that they seem trivial for this example. So let me first start by describing the compactification and to tell you how the rigid limit is engineered geometrically. This Calabi Yau, this P11226, is a K3 fibered Calabi Yau over where the base is P1, and the resulting for dimensional effective field theory is a supergravity theory with three vector fields and two scalars. The period vector is this one. Let me just put it here. And let me just say that x1 and x2 here are small by construction. Now, there is a combination of these two scalar fields that can be taken to parameterize the rigid limit. So the rigid limit here will be just this parameter epsilon sent to 0. What is happening geometrically when this parameter is sent to 0 is that the K3 fiber shrinks to finite volume and the P1 base grows. Now that we have explained what is happening geometrically, we can start checking our decoupling condition. So we can check immediately the charge to mass ratio for our states and realize how some of these are diverging for small values of x1 and x2. So here we see that these are the one for the P2 and the Q2 charges. So these are pointing at these entries of the period vector that are x2 and f2. We also notice how, well, this combination of monodromies, but not only this, all the monodromies, this is just very, is very clear. How also the monodromy only mixes the two central entries of the period vector. And so also another decoupling condition is met. And for the definition we gave before, we can advocate for a core rigid field theory. Well, for who is familiar with this example, there is no surprise here. The rigid theory in question is Seiberg Witten theory. This is supported on the ALE surface on which the K3 degenerates along the limit. In fact, here I want to just, here comes a disclaimer, very short one, that I'm not showing this example, the things I'm showing in this example have been well known for a lot of 30 years. But this is not the point of showing this example. I'm showing this example because here the things are crystal clear. But the claim is different. The claim is this is always happening when we have gravity decoupling. I invite you to check the paper where we discuss many examples that are very different in nature. But okay, after we checked these first two decoupling condition, let's move on and look at the EFT action and its coupling. I was not very specific at the beginning, so let me now tell you what are these conditions that I was talking about. How am I going with time?
I was gonna actually say you have 5 more minutes from now.
Perfect. Okay, so EFT, let's have a look at the EFT condition on the couplings. First one is the absence of kinetic mixing. From the period, we can recover the metric of the moduli-space and the gauge kinetic function. Again, here, don't focus on the explicit expression. I just want you to focus on the fact that there is no mixing, no kinetic mixing between the second direction, that is the one we said we claim is the for rigid field theory, and the other field directions. So from here we can guess no kinetic mixing. And also I want you to focus on the fact that these two entries correctly flow to the same rigid value when we restrict to this subsector, to the rigid subsector that in this case is the direction 2, x2. Here, just one small thing I want to, like that I wrote here, I want to point out. Here for absence of kinetic mixing, we not only mean that the off-diagonal entries for these matrices should vanish, but better than the inverse of the restriction of these matrices is given by the restriction of the inverse. This may okay, this may be confusing, but I just wanted to point this out. You can forget about this last sentence. Let me now tell you about the second condition that we should verify for the EFT couplings. That is asking for no significant interaction that is mixing the core rigid field theory with the other sectors. In particular, here we mean the gaugino gauge boson coupling that is encoded for the Pauli term. So here we see this is the Pauli term. This is an interaction term between the gauginos and the gauge bosons. This is the field strength of the bosons. And so we are asking that this term is not giving significant mixing between the core rigid field theory and the other U1 directions. The interesting thing about this condition is that it can be read under the lenses of the scalar curvature of the moduli space. In fact, we can write the scalar curvature in this, well, maybe scary way, where we also have introduced this notation that simply means that we are in spirit normalizing. We are computing a physical Pauli coupling, normalizing them in this way. And so with this slide, I conclude the presentation, and I do so by presenting this reinterpretation or a refinement of the curvature criterion that claims that the divergence in the curvature can never be generated by normalized Pauli couplings that do not belong to the core rigid field theory. and that the strongest source of divergence is generated by normalized Pauli coupling that only involve the core rigid field theory. So in other words, we are saying that if we factorize, if we rewrite the curvature in this way, now the claim is that this part is never giving you divergence, and that the strongest divergence is always given by this term. That is the Pauli couplings, the physical Pauli couplings belonging to the core rigid field theory. Okay. So let me wrap up. In this work, we are proposing a comprehensive, let's say, picture of gravity decoupling that connects between several concepts. We give a definition for the core rigid field theory that decouples from gravity in terms of monodromies and diverging charge to mass ratio. So both physical and topological terms. But we also present some condition that can be checked at the level of the EFT action, and that should be satisfied to claim the coupling. And we show all this in a wide range of different examples, such as larger complex structure, conifold, let's say conifold-like limits, and Seiberg Witten limits, as I showed you with the example. But with this, I conclude. Thank you for your attention.
Thank you. Are there any questions? Yes? Veran?
Yeah. Hi. Thanks so much for the talk. They're really nice. I have a quick question about the period vector in this Calabi Yau. Is that an integral basis period vector that you have, or presumably
Yes.
it's...
Oh, I will disappear again. Yes. Can you hear me well?
Yes, I can hear you.
Okay. So this is a period vector. Yes. It should be, yes. The only thing is that this basis is non-canonical, in the sense that the basis of cycle do not intersect in the usual way, where the symplectic matrix is 0, 1, -1, 0. It's a multiple of this, but the cycles are, yes, the basis of cycle is integrally quantized.
All right. Thanks. Thanks for that.
Thank you.
Anybody else? So if not, I have a quick one. But so these EFT conditions that you mentioned at the end, and these other, some of them are implied by these other conditions that or restrictions that you. So can you go back to the conclusion slide? You have some EFT conditions, then you have some other conditions above. I don't remember how you call them. Okay, this definition of RFT decoupling. These EFT conditions are implied by some of these definition of, for example, the curvature one and
Good
and
question.
Pauli couplings.
Well, there are implications that are clear. Let me go to the net, let's say, in this thing. The rigid couplings, so the two conditions that I mentioned at the end imply curvature divergence when they are satisfied, imply charge to mass ratio divergence. And well, of course, seeing a monodromy generalization from this is more difficult, but the point is that you could have these two conditions for the EFT couplings satisfied, but then monodromies that do not satisfy, that do not factorize, sorry, and then in our opinion, you shouldn't claim decoupling. So
You shouldn't
claim you shouldn't claim gravity decoupling.
Okay.
So okay.
And now that I see on this map this hierarchy of eigenvalues, did you mention this or then?
Yes, this is very interesting actually, because I mean, a big part of the paper is devoted to these metric essential instantons that I didn't even mention during the presentation. These are instanton correction that are necessary for the coupling not to be degenerate. The clearest example, also give the name to this instanton correction, is the metric. If you don't include some type of instanton correction, the metric is degenerate. So you have to include this instanton correction. And when these instanton corrections are present, these metric essential instanton corrections are present, all this story of gravity decoupling is much, much clearer, in my opinion. So in the sense that you can identify what is the sector of the theory that is decoupling from gravity in a very, very clear way. And all the rest follows, really. The divergence of the curvature and the divergence of charge to mass ratio. And it is because this metric essential instanton correction generate a hierarchy of eigenvalues, because without them, the metric is degenerate.
Okay, thanks. Well, if there's no further questions, then I guess we can go on to the next talk since we're already a bit late. And yeah, let's thank Lorenzo again.